There are things in this universe that exist beyond the comfortable boundaries of human imagination. Objects so extreme, so fundamentally alien to our everyday experience, that even describing them accurately requires us to abandon almost everything we think we understand about matter, space, and time. Before we begin this journey into one of the cosmos's most terrifying creations, if you find value in exploring the true nature of reality through science, consider subscribing and leaving a like. It helps others discover these ideas. Now, let's continue. Imagine for a moment that you could take everything you are, every atom in your body, every molecule that makes up your bones, your blood, your brain, and compress it down. Not just squeeze it tightly, but truly compress it, eliminating all the empty space that exists within and between atoms. The result would be something smaller than a grain of sand. This isn't metaphor. This isn't exaggeration. This is the literal truth about the structure of matter. You are, in a very real sense, almost entirely empty space held together by forces you cannot see, creating the illusion of solidity. And in certain places in the universe, that illusion is not just shattered, but obliterated entirely, revealing what matter truly becomes when compressed beyond all terrestrial limits. Neutron stars represent one of the most extreme endpoints in the life cycle of matter itself. They are not simply dense objects or heavy celestial bodies. They are locations in space-time where the fundamental architecture of atoms has been dismantled and reconstructed into something that barely resembles matter as we know it. To understand why these objects are so profoundly disturbing, we must first understand what matter actually is, how it holds together, and what happens when the forces that maintain its structure are pushed past their breaking point. Everything you have ever touched, everything you have ever seen, every physical object you have encountered in your entire life is made of atoms. This is not news to anyone who has taken a basic science class, but the true nature of atoms, the reality of what they are and how they maintain their existence, is something that often gets lost in simplified explanations. An atom is not a tiny solid ball. It is not a miniature solar system with electrons orbiting a nucleus like planets around a sun, though that image has persisted in popular understanding for over a century. An atom is better understood as a cloud of probability, a region of space where certain particles are likely to be found, held together by forces that operate on scales so small and with such precision that they defy everyday intuition. At the center of every atom is the nucleus, and this is where most of the atom's mass resides. The nucleus itself is composed of two types of particles, protons and neutrons. Protons carry a positive electric charge. Neutrons, as their name suggests, are electrically neutral. They carry no charge at all. Together, protons and neutrons are known as nucleons, and they exist in the nucleus in a tight cluster, bound together by what physicists call the strong nuclear force. This force is one of the four fundamental forces of nature, and it is aptly named. It is the strongest force known to physics, but it operates only across incredibly short distances, roughly the diameter of an atomic nucleus. Beyond that distance, it drops off rapidly to nothing. The existence of neutrons is not accidental. They play a crucial role in the stability of atomic nuclei. Without neutrons, most atomic nuclei could not exist. The reason for this comes down to a fundamental problem with electric charge. Protons, being positively charged, repel each other through electromagnetic force. If you tried to pack multiple protons together into a tiny space without anything else present, they would fly apart instantly. The electromagnetic repulsion between them would overcome any attempt to hold them together. Neutrons solve this problem. They add mass to the nucleus and contribute to the strong nuclear force that binds nucleons together. But because they carry no electric charge, they do not add to the electromagnetic repulsion. They act, in a sense, as nuclear glue, helping to stabilize the nucleus against the mutual repulsion of its protons. In lighter elements like hydrogen and helium, the ratio of neutrons to protons is roughly 1:1 or close to it. As you move to heavier elements, the ratio shifts. Heavier nuclei require proportionally more neutrons than protons to remain stable because the electromagnetic repulsion between protons grows stronger as you add more of them. The strong nuclear force, remember, has a very short range. As nuclei get larger, protons on opposite sides of the nucleus are too far apart to feel much strong force from each other, but they still feel the electromagnetic repulsion, which has a much longer range. More neutrons are needed to provide additional strong force, binding without adding electromagnetic repulsion. By the time you reach very heavy elements like uranium or plutonium, there are significantly more neutrons than protons in the nucleus. But there is a limit to how far this can go. Eventually, you reach a point where adding more neutrons no longer helps. The nucleus becomes unstable no matter what you do. This is why there are no naturally occurring stable elements beyond a certain point in the periodic table. The largest stable nucleus is Lead-208, with 82 protons and 126 neutrons. Beyond that, all nuclei are radioactive. They will eventually decay, transforming into lighter elements through various nuclear processes. The balance between the strong nuclear force trying to hold the nucleus together and the electromagnetic force trying to blow it apart defines the limits of nuclear stability, and these limits apply under normal conditions, the conditions we experience on Earth and throughout most of the universe. Neutrons themselves, when isolated from a nucleus, are not stable. A free neutron, floating alone in space away from any atomic nucleus, will decay in about 15 minutes. It transforms into a proton, an electron, and an antineutrino through a process called beta decay. This happens because a neutron is actually slightly heavier than a proton. The mass difference is tiny, less than 1/10%, but it is enough to make the neutron unstable when it is not bound inside a nucleus. The decay releases energy, which is carried away by the electron and antineutrino, and leaves behind a slightly lighter proton. Inside a stable nucleus, however, neutrons do not decay. The environment of the nucleus, the interactions with other nucleons through the strong force, changes the energy balance and prevents the decay from occurring. Neutrons in stable nuclei can persist indefinitely, as long as the nucleus itself remains intact. This is the state of matter under normal conditions, the conditions that prevail on planets, in atmospheres, in interstellar space, and in the outer layers of stars. Atoms maintain their structure. Nuclei remain stable, or if they are unstable, they decay slowly over time according to well-understood nuclear physics. Electrons orbit in their probability clouds around nuclei, and the electromagnetic force keeps atoms from passing through each other, creating the sensation of solidity that we experience when we touch objects. The strong nuclear force stays confined to the nucleus, doing its job of holding protons and neutrons together, and the universe behaves in predictable ways that allow chemistry, biology, and consciousness to exist. But there are places in the universe where conditions are not normal. There are environments where matter is subjected to pressures and forces so extreme that the familiar rules break down entirely. And it is in these environments that we begin to see what matter truly becomes when pushed to its limits. Stars are crucibles of nuclear transformation. At their cores, the temperature and pressure are so high that atomic nuclei are slammed together with enough force to overcome their electromagnetic repulsion and fuse into heavier elements. This process, nuclear fusion, is what powers stars and produces the energy that makes them shine. In the core of a star like our Sun, hydrogen nuclei, which are just single protons fused together to form helium nuclei, which contain 2 protons and typically 2 neutrons. This process releases energy because the helium nucleus is slightly less massive than the 4 hydrogen nuclei that went into making it. The missing mass has been converted into energy according to Einstein's famous equation, E=mc². That energy radiates outward from the core, creating the pressure that holds the star up against its own gravity. As long as fusion continues, a star is in equilibrium. The outward pressure from fusion energy balances the inward pull of gravity, and the star maintains a stable size. But fusion cannot continue forever. It requires fuel, and eventually, that fuel runs out. What happens next depends on the mass of the star. For stars roughly the mass of our Sun or smaller, the end is relatively gentle. When the hydrogen in the core is exhausted, the core contracts and heats up until it becomes hot enough to fuse helium into carbon and oxygen. The outer layers of the star expand, and the star becomes a red giant. Eventually, the core runs out of helium as well, but the star is not massive enough to heat the core further and fuse carbon. Fusion stops. The core is left as a dense, hot remnant called a white dwarf, supported not by fusion energy, but by a quantum mechanical effect called electron degeneracy pressure. The outer layers drift away into space as a planetary nebula, and the white dwarf slowly cools over billions of years, eventually fading to black. For more massive stars, the process is very different. Stars with masses roughly 8 times that of the Sun, or greater, have enough gravitational pressure in their cores to continue fusion far beyond helium. After helium is exhausted, the core contracts and heats up further, reaching temperatures where carbon can fuse into neon and magnesium. Then neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron and nickel. Each stage of fusion releases less energy than the one before, and each stage lasts for a shorter time. The star builds up its core in layers like an onion, with the heaviest elements at the center and progressively lighter elements in shells moving outward. Hydrogen fusion continues in the outermost shell, helium fusion in the next shell inward, carbon, neon, oxygen, and silicon fusion in successive inner shells. And at the very center, an iron core grows. Iron is the end of the line. Fusion of elements lighter than iron releases energy, but fusion of iron requires energy. Iron nuclei have the highest binding energy per nucleon of any element, which means they are the most stable. Fusing iron into heavier elements is endothermic. It consumes energy rather than releasing it. So when the core of a massive star has converted most of its silicon into iron, fusion stops. There is no more energy source to support the star against gravity. The iron core sits at the center of the star, inert and growing as the surrounding shells continue to fuse lighter elements and add more iron to the core. The iron core is extraordinarily hot, billions of degrees, and extraordinarily dense, far denser than any material on Earth, but it is still made of normal atoms, or rather, at these temperatures and pressures, it is made of atomic nuclei and free electrons moving independently in a plasma. The nuclei are iron-56, the most stable isotope of iron, and they are packed together more tightly than anything in terrestrial experience, but there is still space between them. The core is held up by electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs. Electrons are fermions, particles that obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. When you compress electrons into a small volume, you are forcing them into higher and higher energy states because the lower energy states are already occupied. This creates a pressure that resists further compression. It is not thermal pressure, not the result of heat or motion. It is purely quantum mechanical, arising from the fundamental nature of fermions. For a while, electron degeneracy pressure holds the core up, but the core is still growing, fed by the fusion shells above it, and as it grows, the gravitational force pulling inward increases. When the core reaches a mass of about 1.4 times the mass of the Sun, a threshold called the Chandrasekhar limit, electron degeneracy pressure is no longer sufficient to resist gravity. The core begins to collapse. What happens next occurs almost unimaginably fast. The collapse is catastrophic. The core, which has a diameter of thousands of kilometers, collapses down to a diameter of tens of kilometers in about 1 second. Gravity accelerates the infalling matter to speeds approaching a significant fraction of the speed of light. As the core collapses, the density skyrockets. Atomic nuclei are crushed together. The space between them vanishes. Electrons are forced into closer and closer proximity with protons. Under normal circumstances, electrons and protons do not combine. They are stable as separate particles. But under the extreme conditions of core collapse, something remarkable happens. The energy of the collapse becomes so great that electrons are forced to combine with protons, creating neutrons and neutrinos through a process called electron capture. A proton and an electron merge to form a neutron, and a neutrino is emitted. This process is energetically unfavorable under normal conditions, which is why protons and electrons do not spontaneously merge. But in the collapsing core, the energies involved are so high, and the density is so extreme, that electron capture becomes not just possible but inevitable. Neutrons begin to flood the core. The iron nuclei, which started the collapse, are torn apart. Their protons capture electrons and transform into neutrons. The structure of matter itself is changing. Atoms as discrete entities cease to exist. There are no electron clouds, no nuclei separated by empty space. There is only a sea of neutrons, packed together so tightly that they are essentially touching. The matter has transitioned from a gas of nuclei and electrons into something fundamentally different: neutron-degenerate matter. The collapse continues until the neutrons themselves are compressed to the point where neutron degeneracy pressure, similar to electron degeneracy pressure but involving neutrons instead of electrons, halts the collapse. The core rebounds slightly from this sudden halt, and the rebound sends a shockwave propagating outward through the infalling outer layers of the star. This shockwave, energized by the enormous flux of neutrinos streaming out from the core, blows the outer layers of the star into space in a catastrophic explosion. This is a core collapse supernova, one of the most energetic events in the universe. For a few weeks, the supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion disperses the elements that were created in the star's core, and in the explosion itself throughout the surrounding space, seeding the interstellar medium with the raw materials for future stars, planets, and eventually life. And at the center, where the core collapsed and rebounded, a new object remains: a neutron star. Neutron stars are small by astronomical standards. A typical neutron star has a diameter of about 20 kilometers, roughly the size of a city. But that city-sized sphere contains between 1 and 2 solar masses, the equivalent mass of our entire sun, compressed into a volume smaller than most asteroids. The density of a neutron star is almost beyond comprehension. A single sugar cube-sized volume of neutron star material would have a mass of approximately 100 million tons on Earth. A teaspoon of neutron star matter would weigh about 1 billion tons. These numbers are so large that they lose meaning in everyday terms. There is nothing in terrestrial experience that even remotely approaches this density. To put it in perspective, consider that the density of water is 1 gram per cubic centimeter. The density of iron, one of the densest common materials on Earth, is about 8 grams per cubic centimeter. The density of an atomic nucleus, where protons and neutrons are tightly packed, is about 200 million trillion grams per cubic centimeter. This is already unfathomably dense, but it represents the density of nuclear matter under normal conditions, the density inside an atomic nucleus. The density of a neutron star is comparable to nuclear density, or in some regions even higher. The entire star is essentially a giant atomic nucleus, but instead of containing a few hundred nucleons, it contains about 10 to the 57th power nucleons, most of them neutrons. It is a macroscopic object composed almost entirely of nuclear matter. The structure of a neutron star is layered, and each layer represents a different state of matter under extreme conditions. On the surface, there is a thin crust, only about 1 kilometer thick. The crust is composed of atomic nuclei, but not the familiar nuclei we find in terrestrial matter. These are extraordinarily neutron-rich nuclei, far more neutron, heavy than any stable isotope. They exist in a lattice structure, a solid crystal of nuclei immersed in a sea of free electrons. The density in the outer crust is lower than nuclear density, but still millions of times denser than ordinary matter. As you move deeper into the crust, the density increases, and the nuclei become more and more neutron-rich. At a certain depth, the nuclei become so overloaded with neutrons that some neutrons begin to drip out of the nuclei and exist freely in the spaces between them, forming what is called a neutron drip layer. Below the crust is the outer core, where the density is high enough that nuclei can no longer exist as separate entities. The matter transitions into a superfluid state of neutrons with a smaller admixture of protons and electrons. The neutrons are packed so closely together that they behave as a quantum fluid, flowing without viscosity. The protons, though far outnumbered by neutrons, can form a superconducting state, where they move through the neutron fluid without electrical resistance. This is matter in a state that cannot be replicated in any laboratory on Earth. It is governed by the rules of quantum mechanics and nuclear physics, operating under conditions of unimaginable density and pressure. In the inner core, at the very center of the neutron star, the conditions become even more extreme. The density may reach several times nuclear density, and at this point, our understanding becomes uncertain. The matter might remain as superfluid neutrons, or it might transition into more exotic states. There are theoretical possibilities for matter composed of strange quarks, or quark matter, where the neutrons themselves break down into their constituent quarks. There are models that predict the formation of hyperons, particles that contain strange quarks in addition to the up and down quarks that make up normal protons and neutrons. There might even be condensates of pions or cons, particles that are normally unstable but could exist in stable configurations under these conditions. The truth is, we do not know with certainty what exists at the very center of a neutron star, because we cannot recreate those conditions, and the physics at such densities pushes the limits of our current theories. What we do know is that neutron stars are held together by gravity and supported against further collapse by neutron degeneracy pressure. Just as electron degeneracy pressure supports white dwarfs, neutron degeneracy pressure, arising from the Pauli exclusion principle applied to neutrons, prevents neutron stars from collapsing further under their own gravity. But there is a limit to how much mass neutron degeneracy pressure can support. This limit is called the Tolman-Oppenheimer-Volkoff limit, and it is believed to be somewhere between 2 and 3 solar masses, though the exact value depends on the equation of state of neutron star matter, which is still uncertain. If a neutron star's mass exceeds this limit, neutron degeneracy pressure is insufficient to prevent further collapse, and the neutron star will collapse into a black hole. The gravity at the surface of a neutron star is almost incomprehensible. It is approximately 1 to 2 billion times stronger than the gravity we experience on Earth. If you could somehow stand on the surface of a neutron star, which you cannot for reasons we will explore, you would weigh billions of times more than you do on Earth. A fall from a height of 1 meter would result in an impact velocity of thousands of kilometers per second. The escape velocity from a neutron star, the speed you would need to achieve to break free from its gravitational pull, is a significant fraction of the speed of light, typically around 1/3 to 1/2 the speed of light. This means that light itself, which always travels at the speed of light in a vacuum, is noticeably affected by the neutron star's gravity. Photons emitted from the surface are gravitationally redshifted, losing energy as they climb out of the intense gravitational well. The spacetime around a neutron star is so warped by its gravity that light can be bent into curved paths, allowing you to see around the star, to observe parts of the surface that would be hidden from view if spacetime were flat. This gravitational warping is a direct consequence of general relativity, Einstein's theory of gravity. In general relativity, gravity is not a force in the Newtonian sense. It is a curvature of spacetime caused by the presence of mass and energy. Massive objects like neutron stars create deep wells in the fabric of spacetime, and anything moving through that spacetime, including light, follows the curved paths defined by that warping. Near a neutron star, spacetime is curved so severely that effects, which are barely noticeable in Earth's gravity, become dominant and unavoidable. One of the most disturbing consequences of this intense gravity is the tidal force. Tidal forces arise because gravity decreases with distance. When an object is in a gravitational field, the part of the object closer to the source of gravity experiences a stronger pull than the part farther away. On Earth, tidal forces are gentle. They are responsible for ocean tides, caused by the Moon's gravity, pulling more strongly on the side of the Earth, facing the Moon, than on the side facing away. The difference in gravitational pull is small, and the Earth is rigid enough that the effect is barely noticeable except in the movement of water. Near a neutron star, tidal forces are not gentle, they are catastrophic. Imagine approaching a neutron star feet first. As you get closer, your feet, being closer to the neutron star than your head, experience stronger gravity. The difference in gravitational force between your feet and your head becomes enormous over relatively short distances because the gravitational field is so intense and changes so rapidly with distance. This difference in force would stretch you vertically, elongating your body. At the same time, the gravitational pull is directed toward the center of the neutron star, which means the parts of your body that are to the sides would be pulled inward, compressing you horizontally. you would be simultaneously stretched and compressed, a process sometimes grimly referred to as spaghettification. But the term spaghettification, while evocative, does not capture the full horror of what would actually happen. Long before you reached the surface of a neutron star, the tidal forces would exceed the structural strength of your body by many orders of magnitude. Your tissues, your bones, the molecular bonds that hold your body together would be torn apart. You would be ripped into progressively smaller pieces, reduced first to chunks, then to droplets, then to individual molecules, then to individual atoms, and finally, as you got closer still, even atoms would be destroyed. The electrons would be stripped away from nuclei, and the nuclei themselves would be torn apart by the tidal forces. You would become a stream of subatomic particles raining down onto the neutron star's surface. And if somehow you survived to reach the surface, which is physically impossible, you would encounter an environment more hostile than anything imaginable. The surface of a neutron star is solid, the crystalline crust we mentioned earlier, but it is at a temperature of millions of degrees. The gravity is so strong that any irregularities in the surface, any mountains or valleys, can be at most a few millimeters tall. The gravity simply will not allow the crust to support structures any taller. The surface is scorched by intense radiation, blasted by magnetic fields, and subjected to gravitational acceleration so extreme that time itself behaves differently than it does in the relatively flat space-time we are accustomed to. Time dilation is another consequence of general relativity, and it becomes significant near a neutron star. In a gravitational field, time passes more slowly for an observer deeper in the field compared to an observer farther away. This effect has been measured on Earth. Atomic clocks at different altitudes tick at slightly different rates because they are at different depths in Earth's gravitational well. The difference is tiny, measurable in billionths of a second, but it is real and must be accounted for in technologies like GPS satellites. Near a neutron star, time dilation is not a tiny correction. It is a dramatic effect. If you could hover just above the surface of a neutron star and observe someone far away from the star, you would see them moving in fast forward. Their clock would appear to tick faster than yours. Conversely, someone far away observing you would see you moving in slow motion. Your clock would appear to tick more slowly. The closer you get to the neutron star, the stronger this effect becomes. At the surface, time passes noticeably slower than it does in the relatively flat spacetime far from the star. If you spent 1 year on the surface of a neutron star, several years might pass for someone observing from a safe distance away. You would age more slowly. You would experience less time. This is not an illusion or a trick of perception. It is a fundamental feature of how time operates in curved spacetime. Neutron stars also rotate, and many of them rotate astonishingly fast. When a massive star's core collapses to form a neutron star, the principle of conservation of angular momentum ensures that the rotation rate increases dramatically. The collapsing core is like a spinning ice skater pulling in their arms. As the radius decreases, the rotation rate increases to conserve angular momentum. A star that might have taken weeks or months to complete one rotation can collapse into a neutron star that rotates hundreds of times per second. The fastest rotating neutron stars discovered so far, known as millisecond pulsars, spin at rates exceeding 700 rotations per second. That means the surface of the star is moving at a significant fraction of the speed of light, sometimes as much as 20% of light speed or more. At these rotation rates, the neutron star is oblate, bulging at the equator due to centrifugal force. The equatorial radius is measurably larger than the polar radius. If the neutron star were to spin any faster, it would begin to shed material from its equator because the centrifugal force would overcome the gravitational binding. There is a theoretical maximum rotation rate for neutron stars, determined by the balance between gravity trying to hold the star together and centrifugal force trying to fling material away, and it is typically in the range of 1,000 to 1,500 rotations per second, depending on the star's mass and equation of state. The rapid rotation of neutron stars is intimately connected to one of their most distinctive and observable features, their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe. A typical neutron star has a magnetic field strength of around 1 trillion Gauss. To put this in perspective, Earth's magnetic field is about half a Gauss. A strong laboratory magnet might reach a few thousand Gauss. A neutron star's magnetic field is 1 trillion times stronger than Earth's, and there is a subclass of neutron stars called magnetars with magnetic fields that are even stronger, reaching up to 1 quadrillion Gauss or more. These magnetic fields are generated by the motion of charged particles, primarily protons and electrons, in the neutron star's interior. Despite being composed mostly of neutrons, a neutron star still contains a small percentage of protons and electrons, roughly 1 proton and 1 electron for every 100 neutrons. The motion of these charged particles, combined with the star's rapid rotation, generates powerful magnetic fields through a process similar to a dynamo. The magnetic field is anchored to the neutron star's crust and rotates with it. In many neutron stars, the magnetic axis is not aligned with the rotation axis. The magnetic poles are tilted relative to the rotational poles. As the neutron star spins, the magnetic field sweeps around like a lighthouse beam. Charged particles near the neutron star are accelerated along the magnetic field lines, and as they accelerate, they emit radiation. This radiation, often in the form of beams of radio waves, X-rays, or gamma rays, sweeps past Earth with each rotation of the neutron star. If the beam happens to point toward Earth, we detect a pulse of radiation once per rotation. This is why such objects are called pulsars. The pulse is not the neutron star turning on and off, but rather the beam sweeping across our line of sight, like a lighthouse beam sweeping across an observer on the shore. The regularity of pulsar pulses is extraordinary. The most stable pulsars, particularly the millisecond pulsars, have rotation periods that are stable to better than 1 part in a billion. They are among the most precise clocks in the universe, more stable in the short term than many atomic clocks. Astronomers have used this stability to test fundamental physics, including tests of general relativity, by observing the timing of pulsar pulses with exquisite precision. But the magnetic fields of neutron stars do more than generate radiation. They have profound effects on the matter around the neutron star. Magnetic fields of the strength found in neutron stars and magnetars affect the very structure of atoms. In a magnetic field, the energy levels of electrons in atoms shift, a phenomenon called the Zeeman effect. In the weak magnetic fields we experience on Earth, this effect is small, a tiny shift in the wavelengths of light absorbed or emitted by atoms. In the magnetic field of a neutron star, the Zeeman effect is so strong that atoms are elongated into needle-like shapes, stretched along the direction of the magnetic field. The electron clouds, which normally form roughly spherical or dumbbell-shaped orbitals around nuclei, are distorted into long, thin cylinders. The chemistry of such atoms would be entirely different from normal chemistry. Molecules could not form in the familiar ways. Matter in such a field behaves in ways that have no analog in terrestrial physics. In a magnetar, with its even more extreme magnetic field, the effects are more dramatic still. The magnetic field is so strong that it affects the vacuum itself. In quantum field theory, what we think of as empty space, the vacuum, is not truly empty. It is filled with virtual particles, ephemeral pairs of particles and antiparticles that pop into existence and annihilate each other on timescales so short that they cannot be directly observed. In the presence of a strong magnetic field, the vacuum can become birefringent, meaning light traveling through it behaves differently depending on its polarization. The vacuum essentially acquires properties similar to a material medium. This effect, predicted by quantum electrodynamics, has never been observed in laboratory conditions on Earth because the magnetic fields required are far beyond our current technology. But in the vicinity of a magnetar, it is a real and measurable phenomenon. Magnetars are also responsible for some of the most energetic events observed in the universe, magnetar flares. These are sudden releases of energy, thought to be caused by the rearrangement or cracking of the neutron star's crust due to stresses induced by the intense magnetic field. When a magnetar flares, it can release more energy in a fraction of a second than the sun emits in thousands of years. The radiation from a magnetar flare, predominantly X-rays and gamma rays, can be detected across the galaxy. In one famous case, a magnetar flare from a neutron star nearly 50,000 light-years away, on the opposite side of the galaxy, was bright enough when it reached Earth to measurably affect our upper atmosphere, ionizing parts of it in the same way that a solar flare does. The interaction between a neutron star's magnetic field and any matter in its vicinity can produce spectacular effects. If the neutron star is part of a binary system, orbiting another star, it can pull matter from its companion through a process called accretion. Gas from the companion star is drawn toward the neutron star by gravity. As the gas spirals inward, it heats up due to friction and compression, reaching temperatures of millions of degrees and emitting intense X-rays. If the neutron star is rotating and has a strong magnetic field, the magnetic field funnels the accreting gas toward the magnetic poles. The gas crashes into the neutron star's surface near the poles, creating hotspots that emit X-rays. As the neutron star rotates, these hotspots come in and out of view, producing X-ray pulses. These are X-ray pulses, a type of neutron star binary system where the combination of accretion and rotation creates pulsed emission in X-rays rather than radio waves. Accretion onto a neutron star is not a gentle process. The matter is accelerated to a significant fraction of the speed of light as it falls toward the neutron star. When it impacts the surface, the kinetic energy is converted into heat and radiation with extreme efficiency. The surface temperature at the impact point can reach tens of millions of degrees, and the radiation emitted is predominantly in the X-ray band. The neutron star's gravity is so strong that it can hold onto this material despite the intense radiation pressure. Material piles up on the surface, adding to the neutron star's mass. In some cases, the accumulated material on a neutron star's surface can undergo runaway nuclear fusion in an event called a Type I X-ray burst. The material, primarily hydrogen and helium from the companion star, is compressed and heated by the neutron star's gravity. When the conditions are right, the hydrogen fuses into helium in a sudden, explosive burst. The energy released in the fusion causes the surface to brighten dramatically in X-rays, increasing in luminosity by factors of thousands or even millions within seconds. The burst lasts for a few seconds to a few minutes, then fades as the fusion subsides. These bursts can repeat, occurring every few hours or days as new material accumulates on the surface. There is an even more violent version of this phenomenon, called a superburst. In a superburst, it is not hydrogen fusing into helium, but rather carbon, which is built up in layers beneath the surface, igniting in a thermonuclear runaway. Superbursts release far more energy than ordinary X-ray bursts and last for hours or even days. They are rarer, occurring perhaps once every few years for a given neutron star, but they are far more energetic. The exact mechanism that triggers a superburst is still not fully understood, but it is clear that they represent one of the most extreme nuclear burning processes in the universe. Neutron stars in binary systems can also produce another type of exotic event, a binary neutron star merger. If two neutron stars are orbiting each other, they gradually lose energy by emitting gravitational waves, ripples in spacetime predicted by general relativity. As they lose energy, their orbit decays. They spiral closer and closer together over millions or billions of years. Eventually, they merge in a cataclysmic collision. The merger produces a brief but intense burst of gravitational waves that propagate outward through the universe at the speed of light. When these gravitational waves pass through a detector on Earth, they cause space-time itself to stretch and compress by tiny amounts, which can be measured with extraordinary precision by instruments like LIGO and Virgo. On August 17, 2017, LIGO and Virgo detected gravitational waves from a binary neutron star merger for the first time. The event, designated GW718, was a landmark in astronomy because it was also observed in electromagnetic radiation. Telescopes around the world observed a burst of gamma rays followed by emissions in visible light, ultraviolet, infrared, and radio waves. The observations confirmed theoretical predictions about what happens when two neutron stars collide. The collision itself is almost unimaginably violent. As the two neutron stars spiral together in the final moments before merger, tidal forces stretch and deform them. Material is torn from their surfaces and forms a rapidly rotating disk of extremely hot, dense matter around the merging remnant. The collision likely produces a hypermassive neutron star, a neutron star temporarily supported against collapse by its rapid rotation, though this object is unstable and may collapse to a black hole within seconds or minutes. The collision also ejects large amounts of neutron-rich material into space at speeds approaching a significant fraction of the speed of light. This ejected material is extraordinarily neutron-rich, far more so than anything produced in ordinary supernovae, and in this environment, a process called rapid neutron capture, or the process, occurs. Atomic nuclei in the ejected material capture neutrons very rapidly, faster than they can decay, building up extremely heavy, neutron-rich nuclei. These nuclei then decay back towards stability, producing the heavy elements beyond iron that are rare in the universe. Elements like gold, platinum, uranium, and thorium. It is now believed that binary neutron star mergers are one of the primary sources, possibly the dominant source, of the heaviest elements in the universe. The gold in your jewelry, the platinum in catalytic converters, the uranium used in nuclear reactors. Much of it was likely created in the violent collision of neutron stars billions of years ago, and then dispersed into the interstellar medium, eventually becoming part of the gas cloud that collapsed to form our solar system. The material ejected from a neutron star merger is radioactive and extremely hot. As it expands and cools, it glows, producing a transient event called a kilonova. The kilonova associated with GW7-7 was observed for weeks after the merger, initially bright in blue and ultraviolet light, then shifting to redder wavelengths as the material cooled. The spectra of the kilonova showed evidence of heavy element production, confirming the theoretical predictions. Binary neutron star mergers also produce short gamma-ray bursts. These are extremely energetic bursts of gamma rays lasting typically less than 2 seconds. They are among the most luminous events in the universe, briefly outshining all other gamma-ray sources in the sky. The gamma-ray burst associated with GW1-7 was detected about 2 seconds after the gravitational wave signal, consistent with the merger producing a jet of relativistic particles that emitted gamma rays as it broke through the surrounding material. The jet was likely not perfectly aligned with Earth, which is why the gamma-ray burst was relatively weak by the standards of such events. Had the jet been pointed directly at us, the burst would have been far more intense. The existence of neutron stars and the phenomena they produce challenge our understanding of physics in profound ways. They exist at the boundaries of what is physically possible for matter to withstand before collapsing into a black hole. They involve densities where our best theories of nuclear physics are uncertain. They involve magnetic fields where quantum electrodynamics predicts effects never seen in laboratories. They involve gravitational fields strong enough that general relativity dominates, and time and space behave in ways that have no counterpart in everyday experience. And yet, neutron stars are not hypothetical. They are real, observable objects. We have detected thousands of pulsars through their radio emissions. We have observed X-ray binaries where neutron stars accrete matter from companion stars. We have witnessed gamma-ray bursts and kilonovae from neutron star mergers. We have measured the gravitational waves produced as neutron stars spiral together and collide. The predictions of physics, made on theoretical grounds decades before observations could confirm them, have been spectacularly validated by the actual behavior of these objects. Consider what it means that matter can exist in such a state. The atoms that make up your body, the familiar structure of nuclear and electron clouds, the chemistry that enables life, all of it depends on matter existing at low densities where the electromagnetic force keeps atoms separated and allows them to interact in specific ways. Remove those conditions, compress matter beyond a certain threshold, and the entire framework collapses. Atoms do not just get closer together, they cease to exist as discrete entities. The forces that define chemistry and biology become irrelevant. What remains is neutron-degenerate matter, a state of matter with no analog in terrestrial experience, governed by nuclear physics and quantum mechanics operating at their limits. And this transformation is not slow or gradual. It happens in the final second of a massive star's life, as the core collapses from a diameter of thousands of kilometers down to tens of kilometers, from a state where atoms still exist to a state where they have been obliterated and replaced with a sea of neutrons. The violence of this transition is difficult to overstate. The energy released in the collapse and the rebound, the supernova, is on the order of 10 to the 46 joules, roughly the amount of energy the Sun will emit over its entire 10 billion year lifetime, released in a few seconds. And then the neutron star that remains continues to exist, possibly for trillions of years, slowly cooling, slowly losing its rotational energy, slowly radiating away its magnetic energy. Over time, a neutron star will cool from millions of degrees to perhaps a few hundred degrees, though this takes an extraordinarily long time. Over time, its rotation will slow as it loses energy to magnetic dipole radiation or to the emission of gravitational waves if it is not perfectly symmetric. Eventually, in the unimaginably distant future, a neutron star might become a cold, dark, slowly rotating sphere of degenerate matter, no longer emitting detectable radiation, effectively invisible unless another star or object happens to pass close enough for gravitational interactions to reveal it. But even in this cold, dark state, the neutron star remains an object of extreme properties. Its density does not change. Its gravity does not weaken. If you were to approach it, even billions of years after it formed, you would still experience the same catastrophic tidal forces, the same intense gravity, the same warping of space-time. The neutron star is a permanent scar on the fabric of space-time, a testament to the violence of stellar death and the extremes to which matter can be pushed. There is something deeply unsettling about the existence of neutron stars. They are places where the familiar rules do not apply. They are environments where the assumptions we make about matter and space and time are systematically violated. And they are not distant theoretical constructs. They are scattered throughout our galaxy and throughout the universe, hundreds of millions of them, perhaps billions, each one a sphere of neutron-degenerate matter spinning in the darkness, emitting radiation warping space-time, existing in a state that defies comfortable human intuition. To truly grasp what a neutron star is, you have to abandon the mental models that serve you well in everyday life. You have to accept that there are states of matter so fundamentally different from anything you have encountered that they might as well be classified as something other than matter. You have to accept that gravity can be so strong that it dominates not just the motion of objects, but the flow of time itself. You have to accept that the universe permits extremes far beyond what seems reasonable or intuitive, and that these extremes are not rare or exotic exceptions, but natural outcomes of well-understood physical laws applied to the life cycles of massive stars. Neutron stars also raise questions that remain unanswered. What exactly is the equation of state of neutron star matter? How does matter behave at densities exceeding nuclear density? Are there exotic phases of matter in the cores of the most massive neutron stars? If strange quark matter is stable, can a neutron star convert entirely into a strange star, an object composed of up, down, and strange quarks in a deconfined state? What is the maximum mass a neutron star can have before it must collapse into a black hole? And how does that depend on the details of nuclear physics that we are still working to understand? These questions are not idle speculation. They have real implications for our understanding of fundamental physics. Neutron stars are natural laboratories for testing theories of matter under extreme conditions that cannot be reproduced on Earth. The behavior of matter at nuclear densities and beyond is relevant to quantum chromodynamics, the theory of the strong nuclear force. Observations of neutron stars, particularly measurements of their masses and radii, provide constraints on the equation of state, which in turn informs our understanding of how quarks and gluons, the fundamental constituents of protons and neutrons, interact under extreme conditions. LIGO and Virgo's observations of gravitational waves from neutron star mergers have provided new ways to probe these questions. The gravitational wave signal from a binary neutron star merger contains information about the star's masses and, encoded in the fine details of the waveform as the stars spiral together and merge, information about their internal structure. The way a neutron star deforms under tidal forces during the inspiral depends on its equation of state. By analyzing the gravitational wave signal, physicists can extract the tidal deformability of the neutron stars, a parameter that is directly related to how stiff or soft the matter inside them is. This, in turn, constrains the equation of state. The observations from GWN 7081 SIN provided some of the tightest constraints to date on the equation of state of neutron star matter. They ruled out equations of state that would make neutron stars too soft, too easily deformable, or too stiff, too resistant to deformation. They also provided an independent measurement of the Hubble constant, the rate at which the universe is expanding, by combining the gravitational wave data with observations of the electromagnetic counterpart to determine the distance to the merger and the recession velocity of the host galaxy. This is an entirely new way to measure cosmological parameters using neutron stars as cosmic rulers. Neutron stars also challenge our understanding of general relativity in the strong field regime. Most tests of general relativity have been performed in weak gravitational fields, like the solar system, where the predictions of general relativity differ only slightly from Newtonian gravity. Neutron stars, and especially binary neutron star systems, involve strong gravitational fields where general relativity's predictions deviate significantly from Newton's laws. Observations of binary pulsars, systems where one or both stars are pulsars, have provided some of the most stringent tests of general relativity to date. The orbital decay of the binary system PSR B1716, caused by the emission of gravitational waves, matched the predictions of general relativity to better than 1%, providing the first indirect evidence for the existence of gravitational waves decades before LIGO detected them directly. But there are aspects of neutron stars that push even general relativity to its limits. The interiors of the most massive neutron stars, where matter exists at densities several times nuclear density, are environments where general relativity and quantum mechanics must both be taken into account simultaneously. We do not yet have a complete theory of quantum gravity, a theory that unifies general relativity with quantum mechanics. The cores of neutron stars are among the few places in the observable universe where quantum gravitational effects might be important. Understanding what happens in these cores could provide clues toward developing such a theory. There is also the question of what happens to a neutron star if it accretes enough matter to exceed the maximum mass it can support. Does it collapse directly into a black hole, or is there an intermediate stage? Some theoretical models predict that a neutron star on the verge of collapse might undergo a phase transition, converting into a quark star or a hybrid star with a quark matter core and a neutron matter mantle. Such a transition might release a burst of energy, potentially observable as a unique type of transient event, but we have no confirmed observations of such transitions, and the physics remains speculative. Another unsettling aspect of neutron stars is their sheer prevalence. Every massive star that ends its life in a core, collapsed supernova, if it does not form a black hole, leaves behind a neutron star. Over the history of our galaxy, billions of massive stars have lived and died. Many of them have produced neutron stars. Current estimates suggest there are around 100 million to 1 billion neutron stars in the Milky Way galaxy alone. Most of them are old, no longer active as pulsars, and very difficult to detect. They exist in the darkness, scattered throughout the galaxy, invisible but present, waiting. Some of these neutron stars are moving through space at high velocities. Supernovae are not perfectly symmetric explosions, and the asymmetry can give the neutron star a kick, accelerating it to speeds of hundreds of kilometers per second or more. These high-velocity neutron stars travel through the galaxy, and some of them will eventually escape the galaxy entirely, becoming isolated wanderers in intergalactic space. If a high-velocity neutron star happened to pass through a region of dense interstellar gas, or more disturbingly, through a planetary system, the consequences could be catastrophic for anything in its path. A neutron star passing close to a planet would exert tremendous tidal forces on it. Depending on the distance of closest approach and the neutron star's speed, the planet could be tidally disrupted, torn apart by the differential gravitational pull. If the neutron star passed through a planetary system without directly hitting a planet, but came within a few astronomical units, it could gravitationally perturb the orbits of planets, potentially ejecting them from the system or sending them on collision courses with other planets or into the star. The presence of a neutron star in a solar system, even briefly, would be a disaster. The probability of such an event is extraordinarily low. Space is vast, and even with 100 million neutron stars in the galaxy, the chance of one passing close to any given star system over the lifetime of the galaxy is vanishingly small. But it is not zero, and the fact that such events are possible at all is a reminder that the universe, for all its beauty and order, is also a place of immense danger and violence. Neutron stars are not malevolent. They do not seek to destroy. They simply exist, the inevitable outcome of stellar evolution for a certain range of stellar masses, following the laws of physics without deviation or intent. But their existence is terrifying precisely because it is so indifferent. A neutron star does not care if you approach it. It does not care that its gravity will tear you apart. It does not care that its magnetic field will strip electrons from atoms. It simply is, and if you come near it, the consequences are determined entirely by physics, by the curvature of space-time, by the strength of the gravitational field, by the inexorable operation of natural law. There is also a philosophical dimension to neutron stars that is worth contemplating. They represent an endpoint, a limit to the complexity that matter can sustain under certain conditions. Life, consciousness, intelligence, all of these depend on the complex interactions of atoms and molecules, on chemistry, on structures that can encode and process information. All of this requires matter to exist in a state where atoms can form, where electromagnetic interactions dominate, where the temperature and density are within certain bounds. Neutron stars exist far outside those bounds. There is no chemistry in a neutron star. There are no atoms. There is no possibility of life as we understand it, no possibility of information processing in any familiar sense. A neutron star is a dead object, not in the sense that a planet without life is dead, but in the sense that it is a configuration of matter that is fundamentally incompatible with the conditions necessary for life. And yet, neutron stars are not completely inert. They rotate, they emit radiation, they have magnetic fields, they interact with their environments, they evolve over time. In some sense, they are dynamic systems, just not in ways that bear any resemblance to living systems. They are manifestations of physics operating at extremes, pure expressions of the laws of gravity, nuclear physics, and quantum mechanics, unmediated by the buffering effects of chemistry or biology. Consider also the time scales involved. A neutron star forms in approximately 1 second, the duration of the core collapse. It then exists for potentially trillions of years, far longer than the current age of the universe, which is about 14 billion years. The universe is not old enough yet for any neutron star to have reached the end of its life through purely passive cooling and decay. Every neutron star that has ever formed, assuming it has not been destroyed in a merger or accreted enough matter to collapse into a black hole, still exists somewhere in the universe. They are permanent fixtures, or as permanent as anything can be on cosmological timescales. In the distant future, long after the stars have stopped forming because the universe has run out of gas to make new stars, long after the sun has exhausted its fuel and become a white dwarf, long after the galaxies have dispersed or merged, neutron stars will still be there. They will be among the last remnants of the era of stars, ancient relics slowly fading into darkness, but never truly disappearing. In some scenarios of the far future, neutron stars might be the last large-scale structures to remain before proton decay, if it occurs, disintegrates even them. And if protons are stable, as some theories suggest, neutron stars could persist essentially forever, cold and dark but still present, still warping space-time, still defying the intuition that things should eventually fade to nothing. There is something haunting about that image, a cold, dead universe, empty of stars and light, populated only by black holes and ancient neutron stars, spinning slowly in the darkness, monuments to a time when the universe was young and active, and stars blazed in the night. It is a reminder that the universe does not exist for our benefit, that it will continue long after everything we know is gone, and that the laws of physics will continue to operate, creating and destroying, organizing and dispersing, without regard for meaning or purpose. But we are not at that point yet. We live in an era where stars are still forming, where neutron stars are still being created in supernovae, where the universe is dynamic and active. And in this era, neutron stars are not just ancient relics, but active participants in the evolution of the cosmos. They enrich the interstellar medium with heavy elements. They provide laboratories for extreme physics. They produce gravitational waves that allow us to probe the nature of space-time. They challenge our understanding and push the boundaries of our theories. Understanding neutron stars requires synthesizing knowledge from multiple domains of physics: nuclear physics, quantum mechanics, general relativity, thermodynamics, electromagnetism, and more. They are truly interdisciplinary objects, where no single branch of physics is sufficient to explain their behavior. This makes them difficult to study, but also immensely rewarding. Every new observation, every new measurement, every new gravitational wave detection adds to our understanding and often raises new questions. For instance, the discovery of millisecond pulsars was initially puzzling. Neutron stars are born with rotation periods of tens of milliseconds, and they slow down over time as they lose rotational energy. So how can some pulsars have rotation periods of just a few milliseconds, rotating hundreds of times per second? The answer is recycling. These millisecond pulsars, old neutron stars that have been spun up by accreting matter from a companion star. The accreted matter carries angular momentum, and as it spirals onto the neutron star, it transfers that angular momentum, spinning the neutron star faster. Over millions of years, an old, slowly rotating neutron star can be spun up to millisecond periods. This process also explains why many millisecond pulsars are found in binary systems, often with white dwarf companions. The white dwarf is the remnant of the star that donated the matter, and the neutron star is the recycled pulsar. This recycling process can have strange consequences. If the accretion is uneven, or if the companion star evolves in certain ways, the neutron star might undergo episodes of rapid accretion followed by quiescence. During accretion, the neutron star appears as an X-ray binary. During quiescence, it might become visible as a radio pulsar. Some systems switch back and forth between these states, appearing as an X-ray source for a while, then shutting off and appearing as a radio pulsar, then switching back. These transitional pulsars are rare, but they provide valuable insights into the accretion process and the interaction between the neutron star and its companion. There are also isolated neutron stars not in binary systems, that present their own mysteries. Some of them, the magnetars, have already been discussed. But there are also objects called central compact objects, neutron stars found near the centers of supernova remnants, that emit X-rays but have no radio pulsations and, in many cases, show no evidence of strong magnetic fields. Their properties do not fit neatly into the standard categories of neutron stars, and their existence suggests that there is more diversity in neutron star populations than we initially thought. Then there are R8s, rotating radio transients, which emit sporadic bursts of radio emission rather than regular pulses. The bursts can be separated by minutes to hours, and the timing is irregular. The nature of R8s is still debated. They might be a subclass of pulsars with unusual emission properties, or they might represent a different physical phenomenon altogether. Their irregular emission makes them difficult to study, but they add to the complexity of the neutron star zoo. Each new type of neutron star or pulsar discovered adds a piece to the puzzle of understanding how these objects form, evolve, and interact with their environments. And each discovery reminds us that the universe is more complex and varied than our models predict. We build theories based on what we observe, but the universe is under no obligation to conform to our theories. It will surprise us, challenge us, and occasionally overturn our assumptions. Neutron stars also play a role in the broader context of cosmic chemical evolution. The R process elements produced in neutron star mergers are dispersed into the interstellar medium and become part of the next generation of stars and planets. The Sun and the Solar System formed from a cloud of gas and dust that contain material from previous generations of stars, including neutron stars and supernovae. The heavy elements in Earth, including the uranium in Earth's core and the thorium in its crust, were likely produced in part by neutron star mergers billions of years ago. The gold and platinum we value as precious metals are literally star stuff, forged in the most violent collisions in the universe, and scattered across space to eventually coalesce into planets and be mined by civilizations that arose billions of years later. There is a continuity here, a connection between the most extreme events in the cosmos and the everyday matter that makes up our world. We are, in a very real sense, products of the universe's capacity for violence. The atoms in our bodies, the elements that make up our planet, were created in stellar furnaces and in cataclysmic explosions. Neutron stars, for all their terror and strangeness, are part of the story of how we came to be, and they are also part of the story of how we understand the universe. The study of neutron stars has driven advances in observational astronomy, from radio telescopes capable of detecting faint pulsars from distant pulsars to X-ray observatories that can observe accretion-powered neutron stars in binary systems to gravitational wave detectors that can sense the ripples in space-time produced by merging neutron stars. Each advance in technology has opened new windows on these objects and revealed new aspects of their behavior. The future of neutron star research is promising. Next-generation gravitational wave detectors, both ground-based and space-based, will detect neutron star mergers at greater distances and with higher precision. This will provide better constraints on the equation of state and might allow us to detect new types of signals, such as gravitational waves from oscillations of neutron stars or from asymmetries in supernova explosions. Improved X-ray and radio telescopes will allow us to study neutron star populations in greater detail, discovering more exotic systems and probing the environments around neutron stars with higher resolution. And advances in nuclear physics, both experimental and theoretical, will improve our understanding of how matter behaves at densities approaching and exceeding nuclear density, informing our models of neutron star interiors. There are also speculative possibilities. Could we ever visit a neutron star? Almost certainly not. The radiation, the gravity, the tidal forces, all of them are insurmountable obstacles for any conceivable spacecraft or probe. Even getting close enough to make detailed observations would require technology far beyond our current capabilities. But we can observe neutron stars from a distance, and those observations are enough to reveal their properties and test our theories. In a sense, neutron stars are accessible to us through the information they emit, through the radiation and gravitational waves that carry data about their structure and behavior across the vast distances of space. Could there be objects even more extreme than neutron stars? Yes, black holes. If a neutron star accretes enough matter, or if the stellar core that collapses is massive enough, the neutron degeneracy pressure is insufficient, and the collapse continues past the neutron star stage into a black hole. Black holes are even stranger than neutron stars, regions of space-time where gravity is so strong that not even light can escape, where the curvature of space-time becomes infinite at the center, where our current theories of physics break down entirely. But black holes, for all their strangeness, are in some ways simpler than neutron stars. Black holes are described almost entirely by general relativity. They have no internal structure, no equation of state, no material composition. They are pure geometry, pure space-time curvature. Neutron stars, by contrast, are material objects with complex interiors, governed by a combination of general relativity, quantum mechanics, and nuclear physics. In that sense, neutron stars are more complex, and in some ways, more interesting, even if black holes are more extreme. The study of neutron stars is also a reminder of the importance of theoretical physics. Neutron stars were predicted theoretically before they were observed. In 1934, just 2 years after the discovery of the neutron itself, astronomers Walter Bade and Fritz Zwicky proposed that supernovae might produce extremely dense stars composed primarily of neutrons. At the time, this was pure speculation, based on the application of new knowledge about nuclear physics to the problem of stellar collapse. No neutron stars had been observed. There was no direct evidence for their existence, but the theory made sense, and physicists pursued it. It took more than 3 decades for neutron stars to be confirmed observationally. In 1967, Jocelyn Bell Burnell and Anthony Hewish discovered the first pulsar PSR B999921 using a radio telescope. The regular pulses of radio emission were initially mysterious, but it was soon recognized that they could be explained if the source was a rapidly rotating neutron star with a strong magnetic field, exactly the kind of object that Baden's wiki had proposed. The discovery of pulsars was a triumph of theoretical physics and observational astronomy working together, and it confirmed that neutron stars were not just theoretical curiosities, but real objects that existed in nature. This pattern of theory predicting phenomena that are later confirmed by observation is one of the hallmarks of modern physics. It demonstrates the power of mathematical reasoning and the deep connections between seemingly abstract theory and physical reality. It also shows that the universe, for all its complexity, is comprehensible. We can understand it, at least in part, by applying logic and mathematics, by building models and testing them against observations. But there are limits to our understanding. There are questions about neutron stars that we cannot yet answer. We do not know the equation of state of neutron star matter with certainty. We do not know if exotic phases like quark matter or hyperon matter exist in neutron star cores. We do not fully understand the mechanisms that produce magnetar flares or the details of how accretion onto neutron stars works in all circumstances. These are active areas of research, and progress is being made, but there is much we still do not know, and there is always the possibility that we will discover something completely unexpected. The universe has a habit of surprising us. Every major advance in observational astronomy has revealed phenomena that were not predicted, from the accelerating expansion of the universe to fast radio bursts to the diversity of exoplanets. Neutron stars have already surprised us multiple times, from the discovery of millisecond pulsars to the detection of gravitational waves from neutron star mergers. There is no reason to think we have seen everything they have to offer. Consider, for a moment, the subjective experience of time near a neutron star. If you could somehow survive near the surface, protected from the radiation and the gravity and the magnetic fields by some fantastical technology, you would experience time differently than someone far away. You would age more slowly. Events in the distant universe would appear to unfold more rapidly from your perspective. If you spent what felt like 1 year near the neutron star's surface and then returned to a safe distance, you might find that several years had passed for everyone else. This is not science fiction. This is a direct consequence of general relativity, an effect that has been measured and confirmed in less extreme circumstances, and that becomes dramatic near neutron stars. This time dilation also means that processes happening near a neutron star appear to happen more slowly when viewed from a distance. If a neutron star is accreting matter and something happens on its surface, like an X-ray burst, an observer far away will see the burst redshifted and stretched out in time. The photons emitted from the burst have to climb out of the gravitational well, losing energy and arriving at the observer with lower frequencies and longer wavelengths than they had when they were emitted. This gravitational redshift can be measured, and it provides information about the strength of the gravitational field, which in turn provides information about the neutron star's mass and radius. The interplay between observation and theory in studying neutron stars is intricate. Observers measure properties like pulse periods, X-ray luminosities, gravitational wave signals, and spectral features. Theorists build models of neutron star structure and evolution and predict what those models would imply for observable properties. The two are compared, and discrepancies drive refinement of the models and new observations. This iterative process is how science advances, and neutron stars provide a particularly rich testing ground for this process because they involve so many different areas of physics. There is also an aesthetic dimension to neutron stars. They are, in their own way, beautiful objects. The mathematics that describes them is elegant. The symmetries and conservation laws that govern their behavior have a simplicity that is satisfying. The fact that something as complex as a neutron star can be described, even approximately, by relatively compact equations is a testament to the underlying order of the universe. Of course, this beauty is entirely abstract, a beauty appreciated by those who work with the mathematics and the physics. Visually, a neutron star is not beautiful in any conventional sense. It is a featureless sphere, possibly glowing faintly in X-rays, surrounded by radiation and magnetic fields. But the physics is beautiful, and for those who understand it, that is enough. Neutron stars also serve as a reminder of the scales involved in the universe. The density of a neutron star is roughly 10 to the 14 times the density of water, a factor so large that it is difficult to grasp intuitively. The magnetic field is 1 trillion times stronger than Earth's. The gravity is 1 billion times stronger than what we experience on Earth. These are not incremental differences. They are differences of many orders of magnitude. Differences so large that they represent a transition to a qualitatively different regime of physics. And yet, despite these extreme properties, neutron stars are not the most extreme objects in the universe. Black holes, as mentioned, are more extreme in terms of gravitational strength. Quasars and active galactic nuclei, powered by supermassive black holes accreting matter, are more luminous. Gamma-ray bursts are more energetic per unit time. Neutron stars occupy a middle ground, extreme but not maximally so, complex but not incomprehensible. They are extreme enough to challenge our understanding, but not so extreme that we have no hope of studying them. This makes them valuable. They are accessible laboratories for extreme physics. We can observe them, measure their properties, and test our theories against those measurements. They are not black boxes, completely opaque to observation. They emit radiation across the electromagnetic spectrum. They produce gravitational waves. They interact with their environments in ways we can detect and study. And from those observations, we can learn about the fundamental nature of matter, gravity, and spacetime. There is a certain irony in the fact that some of the most extreme and violent objects in the universe are also some of the most useful for advancing fundamental physics, but this is often the case in science. Extreme conditions reveal phenomena that are hidden or negligible under normal conditions. By studying neutron stars, we are probing regimes of density, pressure, and gravitational strength that cannot be replicated on Earth, and in doing so, we are testing the limits of our theories and pushing the boundaries of our knowledge. The philosophical implications of neutron stars are also worth considering. They exist in a state that is fundamentally incompatible with life and consciousness as we know it. They are examples of the universe creating structures that are, in some sense, maximally inhospitable to the kinds of complex information processing systems that we associate with intelligence. And yet, they are comprehensible to us. We can study them, understand them, predict their behavior. This suggests that the universe, for all its diversity and strangeness, is governed by laws that are accessible to intelligence, that can be discovered and understood through observation and reason. It also raises questions about the limits of what is possible. If matter can exist in the state of a neutron star, what other states are possible? If spacetime can be warped as severely as it is around a neutron star, what are the limits of that warping? General relativity allows for even more extreme curvature, including black holes and, theoretically, closed time-like curves and other exotic geometries. Are these real, or are they artifacts of the mathematics that do not correspond to anything in the physical universe? Neutron stars, by existing and being observable, confirm that at least some of the extreme predictions of physics are real. They give us confidence that the theories are not just mathematical abstractions, but descriptions of actual phenomena. And there is a humbling aspect to all of this. Humans have existed for a few 100,000 years. Recorded history spans a few thousand years. Modern science is a few centuries old, and yet, in that brief span, we have developed the tools and the knowledge to understand objects like neutron stars, objects that exist in conditions so far removed from our everyday experience that they might as well be alien artifacts. This is an extraordinary achievement, a testament to human curiosity and ingenuity, but it is also a reminder of how much we do not know. For every question we answer about neutron stars, new questions arise. The more we learn, the more we realize how much there is left to learn. This is not a failure. It is the nature of science. Understanding is always provisional, always subject to revision in light of new evidence. And the universe is under no obligation to make itself easy for us to understand. Neutron stars are terrifying not because they are malevolent or because they threaten us directly. The nearest known neutron star is hundreds of light years away, far too distant to pose any danger. They are terrifying because they reveal the universe as it truly is, a place of extremes, where matter can be compressed to densities that obliterate atoms, where gravity can warp space-time so severely that time itself slows down, where magnetic fields can reach strengths that alter the structure of the vacuum. They are terrifying because they remind us that the comfortable, stable conditions we experience on Earth are a narrow sliver of what is possible, a fragile bubble in a universe that is, for the most part, hostile to life. And they are terrifying because they exist as a consequence of processes that are, in principle, understandable, but that involve scales of energy and violence that dwarf anything in human experience. A supernova releases more energy in a few seconds than humanity has used in its entire history. The formation of a neutron star involves the compression of a stellar core down to nuclear densities in about 1 second, a process so violent that it produces a shockwave capable of blowing away the outer layers of a massive star. These are not gradual or gentle processes. They are cataclysmic, and they leave behind objects that are permanent reminders of that violence. But there is also something awe-inspiring about neutron stars. They are products of the same physical laws that govern everything else in the universe, the same laws that allow stars to shine, planets to orbit, and life to exist. They are not violations of those laws. They are expressions of them, taken to extremes. And the fact that we can study them, that we can observe them and measure their properties, and compare those measurements to theoretical predictions, is a profound statement about the power of science and the intelligibility of the universe. In the end, neutron stars are both terrifying and fascinating, alien and comprehensible, destructive and informative. They challenge us to expand our understanding, to push the boundaries of what we know, to confront the reality that the universe is stranger and more extreme than our intuitions suggest, and they reward that effort with insights into the fundamental nature of matter, gravity and space-time, insights that would be impossible to gain in any other way. As we continue to observe neutron stars, as our technology improves and our theoretical understanding deepens, we will learn more about these remarkable objects. We will refine our models, constrain the equation of state, discover new types of neutron stars and new phenomena associated with them. We will use them to test general relativity in ever more stringent ways, to probe the limits of nuclear physics, to understand the processes that enrich the universe with heavy elements. And perhaps, in studying these objects that exist at the boundaries of what is physically possible, we will gain insights that extend beyond neutron stars themselves, insights into the nature of the universe and our place within it. Neutron stars are reminders that the universe is vast, ancient, and filled with wonders and terrors in equal measure. They are products of stellar death, monuments to the violent processes that shape the cosmos, and laboratories for physics at its most fundamental. They are more terrifying than you might imagine, not because of any threat they pose to us directly, but because of what they reveal about the nature of reality. They exist in states that defy imagination, governed by laws that operate at extremes, challenging our understanding and expanding the boundaries of human knowledge. And they will continue to exist long after we are gone, spinning in the darkness, warping space-time, silent witnesses to the unfolding of the universe across eons of time.